Hello there. So here we are for the run through of the MAB141 2007 Semester 1 practice exam that I've released on the Blackboard page. So if you're watching this, you've either had a go at the exam, which is good for you, and you can get a feel for how well your thought processes were, or maybe you're just having a look to see the general format. Either way, I don't really mind. So I'm just going to walk through the 6 questions and just talk through perhaps some of the... well, I don't know how this is going to go actually, but we'll see. So let's have a look at question 1. So I'll say again, these questions were stolen off the stats quizzes, which is why they might have seemed familiar for you, but the format is exactly the same as what you're going to see in the final exam, except that the data sets that are used in the final exam, the situations, are not going to be familiar to you, but the information will be there for you to read. Okay, so the relationship between height and arm span measurement was studied in order to assess the use of the arm span measurement as a suitable proxy indicator for height. Researchers wish to know if the average difference between height and arm span is 0 centimeters. Our commander output analyzing this difference, and the difference is defined as height minus arm span, for 174 subjects is given on the following pages. So we've got to choose the test. Now the 3 tests that we've been given here are the one sample t-test, the Wilcoxon sign rank test, or the sign test itself. So it's going to be one of those 3 tests. So the one sample t-test is the most powerful one. We go with that one if we have the assumption of normality in the population. If we don't have that assumption of normality, the next most powerful test is the Wilcoxon sign rank test, which we can use if we have a symmetric distribution of the population. If we don't have that symmetry, then we go with the sign test, which is a very poor test. It's basically just a binomial test counting the overs and unders, just checking if it's 50%. So those are going to be the choices. Let's have a look and make that decision. So the first thing we're going to be thinking about in this question is the data of the population normally distributed? You know, is that possible looking at our sample? So we're going to go down here and we're going to have a look at our data. So you see here, we do have a bit of a problem here and a bit of a problem here. It's not too bad in the middle. It does dip a little bit too low for where it theoretically should be. So this I would call a 50-50 case, because I've said before that this assumption of normality is not as big an issue as the assumption of equal variances that comes in question 2 and question 3. So I call this a 50-50 call. Personally, I would say that this is not good enough, that you have a bit of skewness to the right. You can actually see here, these do match up, right? It's showing you that these ones here, they're just too high. You know, they should be a bit lower. They should be more around about here, those upper values, for it to be normal. And these ones that are down here, they should sort of be more up here. So it seems as if some are skewed way too high and some are skewed way too low. Of course, most people are around about a 0 difference, because that's really what we're testing, whether the theoretical difference could be 0. But I would look at this personally, and I would be saying, for me, I'd say the assumption of normality seems to not hold, because the extreme tail values seemed to be too far on the extreme. The larger values are slightly too high and the lower values are slightly too low. So I would say that the assumption of normality has been broken. If you said that most of the points in the middle are fairly close, yes, some of the higher ones are too high and some of the lower ones are too low, but you're not too concerned about this because the normality assumption is not as strict, so therefore you're going to tentatively accept the assumption. If you said that, fine by me, 4 marks, no problem there. So, okay, we have a decision then. If you're saying that you have normality, that means you can jump to the one sample t-test. There it is. And so you will jump down to here, you'll look at your p-value, there it is. Now that p-value is 9%. Now I don't mind here whether you use the sliding scale system that I set up, so saying that there's slight evidence against no hypothesis, or if you just want to use a 5% cutoff. Either way, I mean 9%, slight evidence means slight evidence is like a little bit of evidence that that the null hypothesis is broken, but it's not really very strong. You don't want to be saying that you're very sure about it. It's maybe, only slightly, maybe, baby. Call Me Maybe, I think, is the song I'm trying to refer to. So even then, it's not really very strong. If you're going for the Wilcoxon-Stein rank test, you can see that the p-value is actually well over 10%, so you don't have any evidence there. But before I get to that, I should talk about what the hypotheses are. So if you were going with the one sample t-test, your null hypothesis here is kind of given away in the question, because it's whether the average difference between height and arm span is 0 centimeters. That's the question. So the null hypothesis here would be that average is equal to 0, that the average difference is equal to 0 centimeters, and the alternative hypothesis would be that it's not 0. This is a two-sided test. We're not looking to show that one is definitely larger than the other here, or that it's either above or below 0. So probably best to explain that by words, I think, in this case. But I've said before, I don't mind if you use the notation. Now that's if you're doing the one sample t-test. For the Wilcoxon-Stein rank test, it's on the median. So it'll be either the median is 0 or the median is not 0. So the hypotheses change depending on the test that you have there. If you're doing the sign test, it would actually be about the value of p, the probability of being above and below the threshold value. So you need to know the differences between the test here and how they're set up and what they're testing on. Okay, so we can see that if you went with either the one sample t-test because you're happy with normality, or if you went with the Wilcoxon-Stein rank test, there's not really enough evidence here. So your answer for part C would be something like the p-value is not low enough. You could say, that there seems to be insufficient or maybe very slight evidence that the arm span is not 0 centimeters. So it looks as if that we can't say with any confidence that there is a significant difference between arm span and height. That's the conclusion that I would be looking for there. Now it says here, also comment on the validity of your conclusions if there are any issues with test assumptions or unusual observations. I'd expect you to do that if you went with the one sample t-test, because you've gone with a bit of a risk here. You'd say, well, there's a possibility that these unusual observations have skewed the result slightly, so we need to take this result with caution. If you've gone with Wilcoxon-Stein rank test, you don't need to worry about it there, because you've dealt with that by going with a weaker test. It also says, if you choose a one sample t-test, explain what the confidence interval means in the context of the study. You don't need to do that if you don't have a significant result, because you're basically saying there's no significant evidence of a difference between arm span and height. So why would you actually say what you think the difference is? Because you're saying, well, it could be 0, it could be nothing. You do actually see that in the confidence interval. The confidence interval that's given will straddle 0. You can see it there. It'll be either side of 0. It could be less than 0, it could be greater than 0. It could be 0. In fact, you'll only get something which is either side of 0 if you get a p-value under 5%, for a 95% confidence interval at least anyway. So that's it. That's question 1. Hopefully that's easy enough to follow. Let's move on then to question 2. So a component of the study from question 1 was intended to deduce if there was a significant difference in heights between males and females, and if so, the size of this difference. Argument output analysing the heights for the two genders is given on the 2 pages. So this is question 2 based on stats 4. This is when you have you have one continuous variable but across 2 groups. So continuous variable and a categorical variable with 2 groups. That categorical variable is obviously gender, and the continuous variable is the height. So these are the 3 tests possible. There's the pooled 2 sample t-test, so that's when you can assume equal variances between the 2 groups. There's the 2 sample t-test, which is when you don't assume equal variance, and there's the Wilcoxon rank sum test. There are 2 versions, one if it's symmetric, one if it's not, but that just changes what the null hypothesis is on. So we need to decide what the test is. So first thing to check will be the normality of the residuals. So let's see what we've been given here. We've been given a comparison between the 2 groups, and just looking already, it looks as though males seem as if they're taller on average than females, even though these are the median values, but it looks as though this is definitely higher than this, so I'm expecting a low p-value with this one for sure. But really what you're looking for here is for the symmetry. You've got symmetric distributions here. So that contributes to the assumption of normality. And we can also see here we have nice data in the bands most of the time. Actually, none of them are outside the bands, maybe one, but you can have up to 5%, which is fine. So I'm looking at that going, the assumption of normality of these residuals looks fantastic. Everything fits inside the bands. We've got symmetric distributions. Nothing is too high or too low. So the assumption of normality is perfect. So I'd want you to say that. I want you to say the box plots look symmetric. The normal quantile plots have all of the data close to the line. This suggests that the assumption of normality of residuals is valid, or it is fine, or it is satisfied, something like that. Now the second thing you need to look for is equal variances. Now in this case, Levene's test has not been given to you. So the only thing you can run off is by comparing the standard deviation of the two groups, and the general rule of thumb is that you're okay if one of them is about you don't want any one of them more than twice as much as the other. These are pretty close, right? So that's quite good there. You can also see the interquartile ranges are equal. That's something more you look at if you had non-symmetric data, but it is still worth noting that these boxes, these interquartile ranges are equal, and even the ranges look fairly equal. So it looks as though the variation that you're getting within each of the groups looks fine. So that's what you'd want to say there. So this is an obvious case where you're going with the pooled 2-sample t-test. If you said that you were going with one of the other two, you would lose marks here, because it's not a 50-50 call in this case. It is obvious that both of the assumptions have been satisfied, so we are looking for the pooled 2-sample t-test, which is the most powerful test that we have. Okay, so that means, before I jump down, our hypotheses. So in this case, we're looking at these two groups. So our null hypothesis would be that the average for males is equal to the average for females. And the alternative hypothesis, because we're not told to look at one way or the other, would be that they are not equal, that the average for males is not equal to the average for females. Those would be the null and alternative hypotheses. Now, what about your conclusion here? Well, I'm expecting a low p-value for this one for sure, just by looking at the data. So we're jumping down to the pooled 2-sample t-test and confidence interval. There it is. We have a ridiculously low p-value, which is saying that this data is practically impossible if they came from populations with the same mean. So this gives us very strong evidence to suggest a very significant difference in the average heights between males and females. And now that we have that, we can quote the confidence interval. What is the difference? Well, in this case, this is saying that we are 95% sure that the average male height is between 10 and 15 centimeters higher than the average female height. That's what the confidence interval is. It's a confidence interval on the difference. Now in this case, it's mu f minus mu m, because R will do this in alphabetical order. So that difference there will be a negative number because mu m is bigger than mu f. So you can just switch the order of subtraction around and get rid of the minus signs. But that's what it's suggesting, that men are on average, so the men from this population are on average 10 to 15 centimeters taller than women. And that is the way to answer this question. You could also say that you have no concerns with any of the assumptions of this test as well, to complete the question. Okay, let's keep moving on. Question 3. Studies have shown that balance problems can afflict those who are long-term drinkers of alcohol. As part of a preliminary follow-up study, researchers decided to investigate the link between balance times using the UST and the amount of alcohol consumed on a general basis for young adults using those 4 categories, with a sample of 179 students. So it explains the UST involves subjects standing on the dominant leg with their eyes closed for as long as possible. Subject's time ends without the lose balance, swivel or hop. So this will happen in the exam as well. You have a bit of background information on what's actually going on. So this is the ANOVA question, right? We have a continuous variable and a categorical variable with more than 2 categories. In this case, 4 categories. So the 2 tests that we're looking for here are either the one-way ANOVA or the Kruskal-Wallis test. So in order to go for the one-way ANOVA, we need the 2 assumptions to fit. We need normality residuals, which you're going to check for, no doubt, and equal variances across the 4 groups. That's what we need basically in order to use the ANOVA test, with equal variances being quite important. If we can't do that, then we go with the Kroskal-Wallis test, which will be a test on medians if we have symmetry, and if we don't have symmetry, it'll just be a test on the distributions themselves. So let's have a look. Let's jump down and see. So already when I look at this, my impression is that the alcohol level is not going to make much difference to balance times. So I can see the 4 levels down there. Of course, I don't say this, it's just my impression. It looks as if now this is the log of the balance times that have been used, but these values seem to be about the same. All of you in your balance test, regardless of how much drinking you do, seem to balance about the same. So I'm expecting here a high p-value. I'm expecting that there's no significant difference here. There will be differences, but I'm expecting it's not significant. I can also probably see here that it looks as if I don't have much symmetry. These are a bit skewed to the right. That one's probably quite symmetric. That's a bit skewed to the right as well. So the assumption of normality may fall down. The normal probability plot will help us out with that. So we have the 4 histograms. You can certainly see with this one, with the often group, that it's a bit skewed to the right. That's that one over there. These are in order. Sorry, that's the rarely group. My apologies. But yeah, so that's a bit skewed to the right. So that's what, 1, 2, 3, 4. That's the order there. So yeah, that's a bit skewed to the right as well. That one as well. This one you can't really tell. This sometimes kind of looks okay up here, but here it looks like we've got a bit of skewness to the right. Now we've already had a log transformation here, presumably to try and fix that. But I'm a bit worried here that normality is not going to be satisfied. So let's jump down. Well, to my surprise, it's actually kind of okay. Got some values here which are a little bit high, some values here which are a little bit low. I personally would say that this is fine by me, this normality of residuals. If we're going to go with this ANOVA, you could say towards the end, you could go a little bit worried that some of the data looked a bit skewed to the right, but the normality plot didn't seem to indicate this. Some of these lower values are a bit high, but you're actually quite often going to get that with a balance test because you can't have a negative balance time. You have a minimum 0 value, so you can expect a little bit of some of those lower values being a little bit higher than what they theoretically could be for perfectly normal data. So I would say that's fine with the normal test. That's probably about 5% of observations that lie outside the band, which is what you'd expect anyway. So I'm calling that okay. The next one is the test for equal variances. So again, the Wien's test hasn't been given, so what we can do is have a look at the standard deviations, which are there. Now, to my eyes, these look pretty close. If you look at the smallest one, 0.8, and the biggest one, 1.4, it doesn't really give us a problem with the one being twice as large as the other. So that looks fine to me. Also, what we look for in this plot here is that the variation that we're getting is about the same. Yes, it's a little bit bigger in this one, but in general, the variation you're getting looks to be about the same, and you can kind of see it here as well. I mean, it's not too bad, the variation you're getting. It's not as if we have one like this where it's incredibly varied, or we have one like this which is really close and bunched together. We do have pretty good variation. So I'd also say here that I'm happy with the assumption of equal variances. I think that's going to work fine for us. So if I was doing this, I'd say, yeah, let's go for it. Let's go for the more powerful test, for the one-way ANOVA, with a bit of apprehension. Slight feels as if it's slightly right skewed, but it's not too bad. Variances are, not perfect. It's never going to be perfect, but it seems fine. So I would go with the one-way ANOVA test there. Now, the null hypothesis here is that all 4 groups have an equal average. So this would be that the average balance time in the never category would be equal to the average balance time in the rarely category, which would be equal to the average balance time in the sometimes category, which would be equal to the average balance time in the often category. Or you could just write down that the average balance time is the same across all 4 categories of alcohol level. So that would be the null hypothesis. The alternative hypothesis would be that at least one of these groups has a difference. Okay, so let's go to the actual output itself. So let's zoom down and see one-way ANOVA. We have, as I suspected, we have quite a high p-value. So that's saying that there's no evidence against the possibility that all 4 groups are the same. In other words, that alcohol level doesn't make any difference on balance time. We've got no evidence here to show that. The differences that we've seen, you can actually see them up here. These are the differences in the sample means. Yes, they're different. It looks as though, oh look, people who drink often have a much longer balance time. Maybe they're just sort of more relaxed. People who never drink have a lower balance time, which is kind of against what you'd imagine. But they are different. But are they different enough? No, they're not different enough. And look, that's fine. That's good to know. It's useful to know, especially if you're someone who drinks or not drinks. I'm someone who not drinks. Maybe I'm the one who got to be concerned because I'm not going to be able to balance as long as some of you heavy drinkers out there. So this is good to know. This is, well, actually no, in my case, I've just proven that it actually makes no difference. So it's good to know that I shouldn't be concerned, and neither should you, by the looks of things. Of course, the variables that we collected, probably aren't the best for answering this research question specifically, because there could be a lot of bias involved with this. But anyway, that's fine. So we would say here, yeah, there's no evidence of any significant difference, and then we can leave it at that. We would mention that slight concern about the skewness in the normality plots, but only slight concern. The variances, one of them was a little bit larger than the other, but really not big enough for any real concern. There will be no need to talk about these values here because we had no evidence of any differences. We're not going to have any significant p-values in the comparisons test, so we don't need to worry about mentioning that. If you did have a low p-value, you would be looking here to see which of the alcoholic levels have a significant difference. In this case here, none of them do, but we don't even need to mention that. And there we go. So that would be the answer to question 3. Let's move on to question 4. Researchers are interested in the relationship between balance using the UST and reaction time. The UST involves subjects standing on their dominant leg, blah, blah, blah. Reaction time involves subjects pinching a ruler with the thumb and forefinger. Yep. Same deal. We're looking at the natural logarithm of balance times, and we're looking at the reaction distances on the following pages. So this is question 4 based on stat 6. So this is the regression correlation question. Now the first thing you want to do here is decide whether this is a causal relationship or not. Now this is not. A causal relationship is when changing one of these values will directly cause the other one to change. And you more get that in an experimental design where you're splitting people up into different categories to see how that affects the outcome, whether change in category is going to cause them to react differently. This is not the case here. It's not as if those who've got a quicker reaction time, because of that quicker reaction time, it causes them to balance differently. It's not that at all. So that actually automatically rules out simple linear regression, because simple linear regression is only for causal relationships. So we're going to be looking either at a Pearson correlation or a Spearman correlation. Now, if you do have a causal relationship, you will go through all of the tests, and if the tests aren't satisfied, you can then still slip into a correlation analysis. That's fine. That's sort of the lower version of the test. But if you don't have a causal relationship, then you shouldn't be looking at a simple linear regression. Now, sometimes that can be controversial, whether it is or not. So just like with other things, if you argue it one way or the other, then that's completely fine with us. But only if it's a 50-50 call. It won't be in the final exam. It will be obvious. Okay, so in my case, I need to make a decision on whether it's a Pearson or a Spearman correlation. So I have a look at the scatter graph to see if I have a linear or nonlinear relationship. Now, because I'm looking at a correlation, I ignore the line of best fit. Completely ignore that, because that's only relevant if you're looking at a simple linear regression. So I can't see any evidence that the data is doing this, or that it's, doing something weird like this. It seems as if the data is generally going in the same direction the whole time. So if there is any correlation present, it will be a linear correlation. So I am going for the Pearson correlation test, and I need to explain that. You'd say there's no evidence of a non-linear relationship. It's not as if non-linear would really be if this was happening, if it's sort of going up and then all going down, something like that. But you can't see that here. Sort of the data is sort of spread up and down as it just sort of moves along from left to right. Even though it gets a bit more spread out here, it's not as if the whole block of data is moving up or moving down. So we're definitely going with a Pearson correlation here. So that would be the test. The null hypothesis for the Pearson correlation test is that the theoretical correlation, which is called rho, is equal to 0. And the alternative hypothesis is the rho is not equal to 0. So what we're looking for in that case, we don't need to worry about all this stuff. This is only relevant for linear regression. That's the assumption of normality of the residuals, which you need to check for. This is the assumption of equal variances that you're checking for here. These are the hat values and the Cook's distances. You can look up information on that if you want to remind yourself on what to look up there. That's all in the lecture scribbles. So we do have here the numerical summaries. So for Pearson correlation, it looks very low. You might remember this from Stats Quiz 3. It looks very low. So it looks as though that that's not going to be different enough from 0 to have a very small p-value. So here we're really jumping. We can skip simple linear regression. We don't need that, or the confidence intervals. We're looking at the Pearson correlation test, and there is our p-value. It's very, very high. So that means we have no evidence at all against a null hypothesis. So that is telling us that the assumption that correlation is 0, completely valid. In fact, what we have here is very consistent with that idea. So we have no reason to suggest any correlation between reaction and balance. None whatsoever. And that's the final answer there. So we don't need to mention about the confidence interval. No need for that, because we don't have any significant evidence in the first place. If you did, then you would say, yes, we believe the correlation is somewhere between here and here. But we wouldn't here, because these are straddling 0. The correlation could easily be 0. We can't say that that correlation is either positive or negative. So that would be the thing you're looking for there. Now there's a lot going on with the linear regression, so definitely look over that to check that, because if simple linear regression comes up on the final exam and you've just done the practice exam, then you could fall short completely, because there are a lot of other things to look for. That's the case with all the questions, though. You want to be prepared for all of the possible eventualities that you have. So let's move swiftly on then to question 5. Hopefully not going too fast for you. Researchers at a book publisher wish to understand the difference in reading habits between males and females. They choose to explore the proportion of young adults who have read at least one Harry Potter book and collect data from 178 individuals. So, question 5, based on stats 7, we're looking at a single categorical variable. This has we're looking at 2 categorical variables here, and we're looking to see if the proportion within each of these populations that have a certain characteristic is the same. So which statistical test are we looking for? Fisher's exact test or the 2 proportion Z test? Now this is a pretty easy one. You might remember from the lecture that if you can use Fisher's exact test, you use Fisher's exact test. The only reason why you couldn't use Fisher's exact test is because the computation is too difficult. So all we really got to go is go down and see if it's there. And it is. There you go. There's Fisher's exact test. So the fact that it's there means you can say, yes, we can use Fisher's exact test because it's available and it's the most powerful test. So that's good enough for me. Now what about the null hypothesis? Well, the null hypothesis here would be that the proportion for females is equal to the proportion for males. The proportion of these populations that have read at least one Harry Potter book, and this will be a 2-sided test, so the proportion for females not being equal to the proportion for males would be the alternative hypothesis in that case. Okay, so let's go down and have a look. So we have a numerical summary here, so you can see what those proportions were. This is the two-way table as was collected, you can see there. We've also given the proportions for each gender, so you can see that 50.9% of males in the sample have read at least one Harry Potter book, and 56.8% of females have read at least one Harry Potter book. So that's a larger number, but is it larger enough to suggest that there is actually a difference between males and females here? That's what we're about to find out, and the answer to that question is no. No, we have a high p-value here, which means there is not enough evidence to suggest a difference between males and females. So we don't have to worry about that. We can all rest easy at night knowing that there is no difference between the sexes when it comes to reading habits when measured in this way. As the question, have you read at least one Harry Potter book? I haven't, actually. My sister's read all of them multiple times, but unfortunately none of those get transferred onto me. I don't think my brother has either. So in my family it's certainly true, but in the general population, according to the way this test was done, there's no significant difference, which is good to know. Good to know. But it doesn't really matter if it's good to know or bad to know. You need to report what you found, what the conclusion of your test is. So again, we don't need to comment on the confidence interval because we don't have a significant p-value. This is a confidence interval on the odds ratio. So all you'd have to do here, you don't have to unravel it back to the probabilities. You would just say that the odds ratio of females compared to males is between this and this. So if you did have a significant p-value, these would either both be above 1 or both be below 1. So when it comes to a ratio, equality is when you have a ratio of 1. So if you have something above 1, that's saying it's top heavy. If it's below 1, that means it's bottom heavy. But in our case, the top and bottom are approximately equal. It's not a significant enough difference. So there we go. That's question 5. So that's a pretty easy one. Now you can see here we are getting a lot of high p-values here, so we're not having to go through and collect, report on the confidence intervals and everything. But that may not be the case in the final exam. Sometimes you get a high p-value, sometimes you get a low p-value. So you've got to be prepared either way to know what to do. So that's one reason why these practice exams aren't a good idea to be your only preparation for a final exam, because it only prepares you for sort of one set of possibilities. And yes, if the same thing comes up, you're fine, but if it doesn't, you're in trouble. So this is just a good example of the kind of thing you could see. Okay, last question, question 6. A recent study from the University of Queensland St Lucia campus revealed that their students' main form of transport for travelling to and from UQ is car, public transport, and sustainable modes according to those percentages. Researchers are interested, as to whether QUT students follow the same proportions of transport mode than their UQ counterparts, and take a sample of 179 students. So now in this section in Stats 8, there are different sets of tests. So this is a question looking at one categorical variable with multiple categories. In this situation, there is only one test that you can do, and that is the chi-squared goodness of fit test. So actually here, there's no option to pick from. But if this was a question with two categorical variables with more than two categories, then you do have the options of Fisher's exact test, or the chi-squared test of independence, or chi-squared test of association. So I'm not going to give you tests which are completely irrelevant because of the number of variables here. So in this case, because it's just one categorical variable, it's the chi-squared goodness of fit test which is given there as an option. So you don't even need to pick the test. You should state what the null and alternative hypothesis is. Well, the alternative hypothesis will be that the proportions associated with our car, that will be 24%. So here PC is the proportion of QT students who travel by car, and the proportion of QT students who travel by public transport will be equal to 59%, and the proportion of QT students who travel by sustainable modes will be 17%. So those are the given set of proportions that you are testing our data against. Our data won't be 24, 59, 17. In fact, our data is 10, 83 and 7. So that's not the same as 24, 59 and 17. Can't remember now. Yes. It's different. Is it different enough to suggest that there is a difference? That the population that this samples come from is not the same as one that's consistent with UQ? Well, we have a look at the Chi-square goodness of fit test, and the answer to that question is yes. That is a significant enough difference. We have a low p-value. Now remember, for these tests in Stats 8, there's no formal way of saying which of the differences are more likely, so we just have to informally say where those differences lie. So we'd say there is very strong evidence to suggest that QT students do travel differently to UQ students, and you'd say something like the proportions travelling by public transport is much higher, 83% compared to 59%. This is an informal observation, and proportions travelling by car or sustainable mode of transport is much lower. And that's where the difference is between the two groups. So just identifying where those differences are informally. Okay, so that's it. That is the little walkthrough of the practice exam. Hopefully you found that useful. By all means, do ask any questions about what I've said on this video on the Facebook group if you want to. If you're going to do that well before the exam, maybe just put a little spoiler message up the top, because there will be some students who don't want to read any information about this until they've had a go at doing it themselves. As we're getting towards the end of the exam, if you're watching this, with a few days to go, then I'm sure it's fine to just ask some questions about it if you want. But like I've said before, don't get caught up on this. Go look at the first video that I released back on Monday, on the 29th of May, which is when I released this video, to see some advice on other things that you should be looking at when it comes to preparing for the final exam. This is a snapshot of a possible exam you could get, but if you've just prepared for this, you might be good for a third of the final exam, but certainly not the whole thing. So you need to look at all possibilities, get all of the assumptions in your head, get it all planned out, and then you'll be good to go. So thank you very much. Hope that was useful. All the best of luck in your final exam, and I'll see you around. Bye.